Today we're going to look at how to graph a system of equations, and these will be linear equations. We'll also take a look at solving a linear system with substitution in a later video. A linear system contains two or more linear equations that have the same exact variables. A solution to a linear system is going to be an ordered pair that solves both equations. So we have an example of a system. 2x plus 3y equals 6, negative 2x plus 4y equals 8. And we're wondering, is 2, 3 a solution to the system? What we're going to do is take that ordered pair and plug it into the first equation. I'm going to say 2 plug in 2 plus 3 plug in 3 equals 6. And solve. 2 times 2 is 4. 3 times 3 is 9. Does that equal 6? No, it doesn't. So 2, 3 is not going to be a solution because it doesn't work in the first equation. It may or may not work in the second equation, but as long as I find that it doesn't work in at least one of them, it's not going to be a solution. So we'll check the next one, 0, 2. So I have 2, plug in 0, plus 3, plug in 2, should equal 6. All right, 6 equals 6, so that works for the first equation, but I want to test it out also in the second equation because it needs to work for both for it to be a solution. Oops, equals 8. All right, so that's 0, this is 8, and 8 equals 8, so yes, this one is a solution because it works in both of the equations. You can also tell if a solution is if an ordered pair is a solution when you look at the graph. If we have two systems of equations, two equations are going to be graphed and they're going to be lines. Wherever my graph intersects, that is a solution. So when we look at this graph up here, that's the ordered pair 0, 2. And when we look back at our previous example, 0, 2 was a solution because that is where our graphs intersect. Where your graph intersects is where you'll find your solution to the system. So we're going to take a look at solving a linear system through the graphing method. And in order to do this, we graph both of the equations on the same coordinate plane, look for the point of intersection, and go ahead and use that point of intersection to verify. Always important to verify. So first we're going to probably want to change this to y-intercept form. So I'm going to go ahead and subtract 3x on both sides first. I'll get negative y equals negative 3x plus 2. And then I have to divide everything by negative 1. So I'll get my first equation to be y equals 3x minus 2. So that's one equation. I'm going to go ahead and graph it using the y-intercept at negative 2. And our slope of 3. I'm going to rise up 1, 2, 3 over 1. Up 1, 2, 3 over 1. And in this case, I'm going to give myself as many points as I possibly can because I don't know where the other equation is going to be graphed yet. So I don't know where I might find the point of intersection. So I'm going to do my best to draw my straightest line and then take a look at my other equation. So I have x plus y equals negative 6. I'm going to go ahead and solve for y. And we'll get y equals negative, and I'm going to put a 1 in front of that x, minus 6. So my y-intercept is at negative 6, so I'm going to go 1, 2, 3, 4, 5, 6 down. And then my slope is negative 1, so that's down 1 to the right 1. And I think you can see where it intersects if I go the opposite direction too. Give myself some more points here. Draw my line. And right there, that's my ordered pair. So that's going to be negative 1, down 1, 2, 3, 4, 5. So that's my solution. It does say always verify that it works for both equations. So I'm going to go ahead and take a moment to do that right now. I'm going to say 3 plug in -1 minus 5 should equal 2. Always plug it back in to the original equation. So let's see, we got -1. Oh, it's not +5, it's -5. Did anyone else see I made that mistake? So let's go ahead and plug that in. So this is going to be minus a -5, which would make it -3 plus 5, and that is 2. So it works for the first equation, and that was a good way to check. I totally graphed it right, but I got the wrong ordered pair. And when I was working it out by plugging it in, it didn't look like it was going to work out. So you always want to go back and check. All right, in my second equation, I have -1 plus -5 should equal -6. And in this case, we get that as well. So it works for both. We've got our solution. Just to confirm verifying, this is exactly what we just did. We took our -1, -5, and plugged it in for both equations. We put that right down at the bottom here of the previous slide. All right, you try. You're going to go ahead and graph these. Let's check in just a minute. First, make sure you have every equation in y equals form, and then graph them. Okay, when you go ahead and solve the first system, you should end up with the first line turns into y equals 4x plus 0. That's the red line. The second equation is y equals 2x plus 2. That's the blue line. And they intersect right up here at 1, 4. For letter B, the top equation turns into y equals x plus 1. That's my red line. And then my second equation turns into y equals -2x plus 4. That's my blue line, and it intersects right here over at 1, 2. For letter C, our top equation turns into y equals x minus 5. That's the red graph. Our second equation is y equals -3x plus 3. That's the blue one. And that intersects at 3, -3. Sometimes we will have one solution if our lines intersect. Sometimes we will have no solutions, and this will be a case when we have parallel lines. And sometimes we'll have what's called infinite many solutions, and this is where we have two equations that when we solve for y turn out to be the exact same equations. So when you graph them, you're graphing them right on top of itself, so it shares all of its points, which is why we say infinitely many solutions. So to review our summary here, we have linear systems are two or more linear equations with the same variables. A solution to a linear system are coordinates of the intersection of the lines of the system. To solve by graphing, we graph both equations on the same plane, find that point of intersection, and then verify the point of intersection.